Hey everybody, here's a couple more questions. These are questions 14, 15, 16, and 17 from the final exam from the fall of 2018. I just wanted to walk through these. Question number 14 is a nice nomenclature question, and it's a nomenclature question that's very similar to the question number 13, but it's kind of in the opposite direction. What we're looking for here is what is the ionic formula, or what is the formula for ionic compound that is iron 3 bromide. In order to answer this question, you have to be able to place the bromide on the periodic table. And one thing that you should know about bromide is it is a halogen, and it will very easily ionize to Br minus plus a single electron. So you're looking for Br minus. That's a single negative charge. This says the correct formula for iron 3 bromide is what? Okay, so that 3 in parentheses indicates that iron has a positive 3 charge. Oopsies. So what we want to do is we want to write Fe3 plus Br minus, and our charges are simply going to swap. So this 3 is going to become a subscript for the Br, and this 1 right here becomes a subscript for our iron. Okay, so ultimately we come up with FeBr3. So our answer options: D is out, C is out, B is out, A is the opposite of what we're looking for, so E is our only really good answer options for that. Okay, now question number 15. A 31.5 milliliter aliquot of an unknown concentration was titrated with 0.0134 molar sodium hydroxide. It took 23.9 milliliters of the base to reach the endpoint of the titration. The concentration of the acid was blank. Okay, so this is a titration question, and this is very similar to the previous question that we had. We had one that was H2SO4 neutralized by sodium hydroxide. Well, this is HNO3. This is nitric acid. That's a monoprotic acid. So what we want to do is write our balanced equation. HNO3 plus NaOH. This is going to yield H2O plus NaNO3. Okay, so there are products. Now we have to ask ourselves, is it balanced? Look at our sodiums. Na. Well, there's one sodium on the reactant side, one on the product side. Hydrogens. There's one in HNO3 and one in NaOH. So that's 2 hydrogens. There's 2 hydrogens on our product side. NO3, that doesn't change the ratio there. That's still a nitrate ion. NO3, there's one there's one NO3 on the reactant side and one NO3 on the product side. So we are actually balanced. And so what that means is if you have 1 mole of HNO3, it will react with 1 mole of sodium hydroxide. So that's something to keep in mind for this problem. If we have 50 moles of HNO3, we need 50 moles of sodium hydroxide. So this question says we have 31.5 milliliters of HNO3. I'm going to immediately change that to my volume in terms of liters, so 0.0315 liters of HNO3. That will react with 0.023, that's a 39 liters of NaOH. Okay, my concentration for NaOH was 0.0134 molar. So when I take my concentration of my sodium hydroxide and multiply it by my volume of sodium hydroxide, 0.0239 liters times 0.0134, that gives me 0.0003226 moles of NaOH. Now the great thing about knowing that this is a 1-to-1 ratio is we know that if we used 0.0003226 moles of sodium hydroxide, that means we neutralized 0.0003226 moles of HNO3. So we could set that up in dimensional analysis, 0.0003226 moles of NaOH. Draw a line. Here's our 1 mole NaOH. 1 mole will be neutralized by HNO3. And I come up with, well, 0.0003226 moles HNO3. Now you need to take that in order to get a concentration. Take that 0.0032026. That's the number of moles, and our volume is 0.0315. So we divide our concentration by our volume. So I'm going to switch to a different color. I'm going to switch to green. So that many moles of HNO3, 0.00315 liters of HNO3, and we are left with 0.010166981. Obviously, that's way too many significant figures. We look at our best answer options here. 0.0101, that's our concentration. If you look at answer option A, that's kind of attractive because that gets to 1.02. Well, you would end up at that if you messed up on your volume calculations. But we did our volume calculations right, so that's out. 0.204, that's the diprotic acid. 0.227, I'm not really sure what is there. D would be basically a factor of 50% off, and we are left with answer option E as our only good answer option. So we'll proceed on. Question number 16. The amount of gas that occupies 60.82 liters at 331.03 Celsius and 367 millimeters mercury is blank moles. So this is an ideal gas equation question. PV equals nRT. Do we have our pressure? Yes, we do. Do we have our pressure in our right units? No, we do not. We have our pressure in millimeters mercury. What we need to do is we need to take 367 millimeters mercury and divide it by, well, 760 millimeters mercury, because that is our conversion to get us to atmospheres. So 367 divided by 760 equals 0.483 atmospheres. Okay, next up, our volume. Our volume is in liters. That's exactly what we want, 60.82 liters. Okay. Next is our number of moles, N. That's what we want to solve for. So we're going to rearrange this equation. PV over RT equals N. So now we've got our P, we've got our volume. Our R value is 0.08201. We got that. Our temperature is the last thing. Our temperature is measured in degrees Celsius. What we need to do is convert that to Kelvin. So 31.0 plus 273.15 will get us to Kelvin. 31 plus 273.15 equals, temperature is 304.15 Kelvin. Okay, so now we've got all the numbers that we need. Now we can go ahead and plug all these guys in. We have to make sure that we're using the right units for the ideal gas equation. I'm going to do 0.483 times our volume, 60.82. All right, divide that by 0.08201 times 304.15. All right, and I get an answer of, whenever I plug all that in, 0.483 times 60.82 divided by 0.08201 times 304.15 equals 1.177, which I'm going to go ahead and say is 1.18. Cross that guy out. My answer options: 894, no. 0.850, no. 11.6, no. 0.120, no. We are left with E as our only answer option that resembles what we're looking for. Okay. Now question number 17, the last one we've been covering this little block here, is a gas in a 325 milliliter container has a pressure of 695 torr at 19 degrees Celsius. There are blank moles of gas in this flask. Hey, this is another PV equals nRT. Okay, there are blank moles, so we're looking for N. So we're going to rearrange the ideal gas equation. PV over RT equals N. Okay, N is what we were solving for. Do we have our pressure? Yes, we do, but we need to convert it. 695 torr. Well, 1 torr is equal to 1 millimeter mercury. So 760 torr is equal to 1 atmosphere. So 695 divided by 760 equals 0.914. Okay, next up is my volume. My volume is going to be, I'm going to start writing this equation, 0.914. My volume is 325 milliliters, which I will convert to 0.325 liters. My R is my constant, 0.08201. Got that. And then, let's see, my R value is 0.08201. Temperature, my temperature is 19 degrees Celsius, so 19 plus 273.15. That's going to be 273.15 plus 19 equals 292.15. So, point, plug all this into my calculator, but that's basically the structure right there. 0.914 times 0.325, close parentheses, divide that by, open parentheses, 0.08201 times 292.15, close parentheses, and there we are. I ended up at 0.01239. Okay, so my answer options. 12.4, close, it's off by a factor though. 80.6, nope, E is out. I'm left with 1.48 and 1.24. Well, 1.24 times 10 to the minus second is basically this exact same number, but we're using scientific notation because we're moving the decimal place 2 points, so 1.2. And when we round up to the proper number of sig figs, we are going to get 1.24 times 10 to the minus second. So D is our correct answer there. All right, I hope this was helpful. I'm going to come back to some more problems in just a little while.